Hello, am I audible?
Yes, you are
Yes,
audible.
it is audible, sir.
Okay, so can we start?
So, first of all, very good evening to all of you. I, Dr. Vishal Kumar Gaur, faculty in Department of Electrical Engineering, MNIT, Allahabad. On behalf of organizing committee of this faculty development program on grid resilience and adaptive control evolution in power systems, I extend a very warm welcome to all the participants joining us for this faculty development program. We are truly delighted to have with us our esteemed speaker, Dr. Shailendra Kumar, joining us online from the IIT Bhilai. A very warm welcome to you, sir.
Thank you, sir.
So,
Thank you.
before we begin with the session, allow me to introduce our esteemed speaker, Dr. Shailendra Kumar. Dr. Shailendra Kumar is currently working as an assistant professor in the Department of Electrical Engineering, Indian Institute of Technology, Bhilai, IIT Bhilai. He received B.Tech degree in Electrical and Electronics Engineering from Uttar Pradesh Technical University, Lucknow, India in 2010, and M.Tech degree in Power Electronics, Electrical Machines and Drives from the Indian Institute of Technology, Delhi, IIT Delhi in 2015. He has completed his PhD degree in Department of Electrical Engineering from IIT Delhi in May 2019. He has worked as a postdoctoral research fellow at Petroleum Institute of Research Center, Khalifa University from May 2019 to November 2019. He has also worked as an assistant professor at Maulana Azad National Institute of Technology, that is MANIT Bhopal, from June 2020 to May 2023. He has successfully completed 6 research projects funded by various agencies like DST, NamePad Phase 3, MPCST, and IBITF as a project investigator and co-investigator. Dr. Kumar has been part of 2% World's most cited scientists list published by Stanford University for the year 2024, 23, 22, and 21. Dr. Kumar is recipient of prestigious Osoko Power System Award in Masters as well as in doctoral category in 2016 and 19 respectively. He is also a recipient of Professor Somnath Mahinder Student Travel Award for the IEEE PEDS PADAS 2018 conference and IEEE UPCon Best Paper Award in 2016 and 18 respectively. Dr. Kumar is a senior member of IEEE and member of Indian National Academy of Engineers Society. His research interests include charging stations for EVs, power quality, grid integration of renewable energy sources, custom power devices, and microgrid. So we are fortunate to have him share his insights with us today. So I request Dr. Shailendra Kumar to kindly enlighten us with your lecture. Thank you, sir.
Thank you. Thank you for the nice introduction, Vishal sir. And one more thing I wanted to mention here, like my uh, throat is not okay. I mean, I have sore throat, so for next 1 hour, please bear with me. I mean, whenever you are finding like you are not able to get whatever I'm telling here, please let me know. I'll repeat that particular thing again and again. So I mean, let me share my slide and then we shall discuss the things for. So actually, I have two particular plan for this lecture. One is like theoretical plan. So I'll discuss the basic concept of the topic which I have chosen, like adaptive control, how we can use these intelligent adaptive control. All right, industry is still, they are using this ABC to DQ based control or DQ control. And not only in case of grid connections or grid integration of renewable energy resources, but in case of even though electrical drives as well. So if you talk about the electrical drive, still people are using this ABC to DQ and then DQ to ABC, and then further they are going with the control for motor drive. So these Park and Clark transformation, they are very, I mean, standard kind of control, but there are some demerits which we'll discuss in this particular lecture, and why we need this intelligent control or adaptive control for grid integration. That I'll discuss in this 1.5 hour. And the next plan, or plan 2, I would say, for this lecture, I'll show you one simulation model. As I mean, I have gone through the the brochure of this particular FDP. So in this, they have mentioned, like organizer had mentioned, like it is a kind of I would say that the combination of theoretical part plus some of few concepts which will be discussed in the MATLAB Simulink as well. So I have one MATLAB model related to this seamless transitions. How do we achieve this grid integration, as well as how do we transfer this mod switching from like if you talk about a grid connection. So how do we do this or achieve this grid connections, and how do we transfer the system from grid connected to standalone, as well as standalone to grid connected. So that is basic idea about this talk. So let me share my slides, and then I shall talk about the rest of the thing. So let me go to the screen sharing, and then we can go with the PPT. So I hope this screen is visible, right? And it is also moving.
Yes, sir. Yes, sir.
Yeah,
Yes,
thank you. So idea of this particular title of this talk is Intelligent Adaptive Control for Seamless Renewable Grid Integration and Power Quality Enhancement. So as I told you, there are 3 basic part of this talk. The first one, how do we seamlessly transfer the system from standalone to grid connected and grid connected to standalone? That is the basic requirement. I mean, under Indian grid condition, you may see there are lots of fluctuations, right? The grid it is not available, even though in case of rural areas it is not available 24 hours. Sometimes 6 hour grid is not there, and then I mean regular fluctuations is it has been realized in urban grid conditions. So what we are going to do here, we are developing a system which can seamlessly transfer to the grid connected mode, as well as we realize like the grid connections or the grid is disappeared. Under that conditions, we will seamlessly transfer the system to the standalone. What is the idea? To transfer the system to standalone and grid connections. The idea is to supply uninterrupted power to the local loads, right? So if we have certain kind of inverter over there, right? If I'm talking about the renewable energy source, like we have some PV array over here, and this PV array, it is supplied or it is connected through this converter, which is the 3-phase. Let's suppose 3-phase converter you have considered. So 6 switching signals are there. And then this converter, it is connected via these filter inductors to the AC grid, right? To the AC grid. Now the question is, how do we achieve this grid connections, right? So what people they have done, they have operated this converter in grid connection mode or grid connected mode, right? And then they have operated this system in standalone mode. right? This converter itself, they have operated in standalone mode. What is the need of this transformation or this switching from grid connection to standalone as well as to standalone to grid connection? Because sometimes, or I mean, not sometimes, most of the time you will realize here the load which we are going to connect, that load require continuous power supply, right? Load, we cannot say consumer loads like we will provide only for 6 hour, 8 hour supply to your loads. These loads, if you want to have certain appliances, these appliances requires continuous supply. So what we will do, we cannot depend only on the grid, right? So this system must be capable to operate in standalone mode as well. If there is grid, then it can be connected with the grid. So suppose X amount of power it is coming here, Y is going to the load, and so rest of the power X minus Y, that can be fed to the grid. Right? So this way we can have the power distribution when the grid is there. Now suppose grid disappeared. What will happen? In that case, if grid disappears, under those conditions, suppose you have X amount of power which is coming from the PV array, and this load is varying throughout the day. Obviously, generation is also varying, but load is varying throughout the day, right? You may have load curve and you might have realized like this. This could be, I mean, generation could be like this, but it is hardly, I mean, to realize this load curve. Load is fluctuating, load fluctuation is there throughout the day. So what we have to do, how do we match this generation from the load demand? That is the question is. In a small system, like if you have 5 kilowatt, 10 kilowatt system, it is quite easy to match the load demand. But in the systems like megawatt level or some higher power level, it is quite difficult to match the load demand with the generation, right? So for a small system like 5 kilowatt, what we can do, if suppose now let's go to the numbers. If 2 kilowatt power is required for this load and we are generating 5 kilowatt, how do we match this generation from the load demand? So to match this load demand, if grid is not there, if grid is there, then that rest of the power like 3 kilowatt we can feed to the grid. But what would be the option during when you have this small system and 5 kilowatt generation is there during standalone? So that is the challenge while we are going to transfer this grid connection system, grid connected system to the standalone. Now the question is, how do we achieve it? I mean, obviously, in that case, if load demand is lesser than the generated power or generation, we will lose some of the generation, right? So that's why grid connection is very essential, right? So in that case, what people are doing, they have the concept of MPPT, right? They have the concept of MPPT, and this MPPT algorithm always try to operate at this point, right? This will force the PV array to operate this particular generation or this PV array operate at this MPP point, right? Now, if you want to match this generation with the load demand, this point has to be shifted, I mean, either at the left side or right side. So if I'm shifting this point at the left side, I'm moving to the short circuit condition. So I cannot move this point to the left side. So what people are doing, they are moving this point at the right side and they are getting lesser generation. So what they are doing, they are taking the load current or load parameter as a feedback to this PV, and this once the system is moved to the standalone mode, the generation itself, it drops due to off MPPT mode. So there is algorithm which is known as off MPPT mode or load following converter, load following algorithms, we can say. Whatever the load demand is there, according to that, obviously, as the power plant is rated for 5 kilowatt, it cannot supply power more than 5 kilowatt. So we have to take care, like load will not go beyond 5 kilowatt. Otherwise, this source will not be able to supply that amount of power. But yes, up to 5 kilowatt, it can supply on this load. Right, so we can operate in off MPPT mode, and the generation itself, it is reduced and it can match the load demand. Not only we can reduce to 3 kilowatt or 2 kilowatt, any load power, right? Certainly, after some time, the load is reduced to 1 kilowatt, right? So it will supply only 1 kilowatt power. Correct. So lesser amount of power or the lesser load demand that can be fulfilled, but as soon as it is going beyond the generated power, we need extra source, or we have to increase the number of series, or I mean not series, parallel modules, I would say, because if you add the panel in parallel, then the current rating can be increased because you have to match the voltage rating here. Right, this converter will operate in sync with the input as well as output voltage. So by choosing 415 volt grid voltage here, what I have to do? I have to choose an appropriate value of DC bus voltage. I cannot choose any value of DC bus voltage here. This will be decided based on the grid voltage. So if 415 you have chosen, you have to choose the appropriate like 700, 800 volt DC bus. If you have chosen single phase 230 volt grid here, you have to choose 400 of that particular value of voltage here. So that is the concept of this particular grid connections over here. Now, what are the basic requirements during grid connections? So anyone who can tell me what are the basic requirements during this grid connection? So I prefer to have some interactive session instead of having a one-way communication. I would prefer, I need some answer from the participants as well. I mean, it is the good way, like the active discussion. Otherwise, one-way talking, that is really difficult, at least for me. I mean, I don't know others, but for me, it is very difficult having a discussion, one-way discussion. So anyone who can tell me what are the conditions to have these grid connections? Like if I want to have, suppose I brought one, I can tell you one condition. Suppose I brought one solar inverter, right? From market, I bring one solar inverter. Now, this solar inverter is nothing but it has some PV panels, and then again I'm drawing this unit. So single phase converter, like it is there, right? Some IGBT or some MOSFET modules are there. And now what I have to do, I have a socket of this at my home, right? And now I want to connect this inverter with the socket. What are the basic essential things to this? This is the raw inverter. Let me tell you, I mean, this is not a kind of inverter. It is not a black box, right? You have a devices, you have a panel. Now you wanted to connect with the grid. This is your single phase socket at home or single phase grid at home. What would be the basic essential thing if I want to connect this inverter, solar inverter with this grid? What would be the essential thing? Anyone?
Frequency must be same.
Yes.
Frequency must be same, sir.
Frequency must be same. Okay. Which frequency?
Inverter output frequency and grid frequency.
Yes. So inverter output frequency must be same with the grid frequency. So what is the grid frequency? That is 50 hertz,
50 Hz.
right? 50 hertz.
Yes.
And any other parameter which we need to match with the output and this grid, or only frequency? Do we
Phase
need to
angle.
match other parameters? Yes.
Phase angle, sir. Phase angle.
Phase angle, correct? Phase angle. Only two parameters, or third one also?
Voltage.
Magnitude,
Magnitude of
right?
voltage.
Magnitude of voltage. Right. So let me tell you, there is one standard that is known as IEEE 1547, if I'm not wrong. So this has given these three parameters. If you want to connect your inverter with the grid, you have to match the inverter output with these parameters. It is not like that you are generating some other voltage, frequency, and angle, and you can connect this particular inverter with the grid. No. So if you brought one inverter or purchase one inverter, if you are putting directly to this unit, this will not function. Right? Simply, I brought some raw inverter, raw solar inverter, and I plug into the grid, and you can think like it start generating the power and start injecting the power to the grid. It won't be. So what IEEE 1547 has given, like if the inverter output voltage, let's suppose it is a VI, here we have source voltage or grid voltage VS, theta I, which has been there at the inverter output side, and then we have some frequency like inverter output frequency. Similarly, at the grid side, we have Fs, or we can say theta S and Fs. So here what they are saying, this I mean magnitude which we are talking about, this should be within the limit of this VI
అదేం లేదు
must
మేడం,
be
నాకు
within,
అందరూ ఒకటే. అది మీకు కాంటాక్ట్ లో ఉండరు కదా.
right? It should be within the limit of this. Correct? So I'm talking about in per unit. So it should be, I mean, greater than 0.88, I mean lower voltage, and higher voltage it should not be more than 1.1 per unit. Similarly, for theta, the difference between theta S and theta I and theta S, that must be less than 3 degree. Right? The voltage angle of the inverter and the voltage angle of the grid. So difference between them must be less than 3 degree. Right? There should not be any phase angle difference between these two quantities. And then we have frequency. So people are taking different norms, like the difference between Fi and Fs must be less than, I mean, it is varying depending on the voltage level, as we are going for, I mean, different voltage levels. So generally, we are talking about plus minus 3 hertz, not more than that. It is even more, but I mean, it should not be more than 0.3 hertz variation in the frequency as well. Now, the question is, how do we get this frequency and phase? So, we don't have any frequency sensors or phase angle sensor over here, right? What is given? We have voltage sensors and current sensors. We can sense the voltage and current here. So how do we get this voltage and frequency, by the way? How do we get this frequency and phase angle? Yes, magnitude we can get. We can sense the voltage at the converter output side, and we can sense the voltage or the parameter at the grid side. Both the side we can sense. And we can take the difference, then we can get the magnitude, what is the actual magnitude, whether it is between 0.88 or and 1.1 per unit, or it is going beyond this particular limit. If it is going beyond this particular limit, you are not able to synchronize your converter with the grid. So it will operate in a standalone mode, right? So all these three conditions must be satisfied, right? 0.88, I mean, the magnitude must be within this limit, theta must be within this limit, and frequency must be within this limit. Now, my question is, how do we get this frequency in phase? So we need synchronization unit. Without synchronization unit, we are not able to connect our system with the grid. Correct? So for that, you might have seen various PLL techniques people are using. So what is the input for PLL? Simple voltage they are sensing. So sensing a voltage, it is quite easy. You can sense the voltage by applying some voltage sensor. You can place a voltage sensor here. You can get the voltage magnitude, and this PLL will provide this frequency and phase of this Vs. So you can get the theta as well as information of frequency. Similarly, you can apply to the load voltage as well. Load voltage or converter output voltage, right? Converter output voltage. So you can get these two theta as well, theta I, Fi here, Fs, theta S. So as soon as we got these two units, then we can differentiate it. I mean, we can have a difference between them, and then we can monitor these parameters continuously. So one of the aspect, like how do we go for the seamless transition, right? We need to synchronize our converter with the utility grid. Without synchronization, it is not possible to bring a solar inverter and connect it directly to the grid. So synchronization is one of the very important unit in case of solar.
Load balance. We have this connectivity issue usually comes. But
Now,
whatever
the
reason, I think it is still running in the background, but in your plan, it's saying success.
Can you mute yourself? Somebody is creating some noise.
Like usually, whether we have seen this is the new extractor, not the first time we are saying this. Yeah. New extractor is creating all sort of problems. I think we have to do more testing. We can't take this live. Yeah, it's very tough.
I'm not able to mute this person.
Okay, please tell you.
Can you mute this? Lakshit?
They changed a common. After that, only it is so many issues. The common
Give me
library, right? Common sandbox,
the
GCP.
access to mute.
Yeah,
After that, only
Okay.
we got this.
And
Can
we
you
got
mute
many
yourself?
duplicate issues as well, Rajesh. And they pointed a old
Okay, so this way we have this kind of seamless transitions or synchronization of a converter with the utility grid, right? Other part, apart from having this grid connections, what we have addressed. So this was the one of the, challenge which we have addressed in our, what we can say in our research, what we have done. The second thing which we have addressed, that is the power quality issue. Right? The first one we have addressed the seamless transition. So in case of power quality issues, what people are saying like this converter, it is utilized as a solar inverter. And while we are doing from DC to AC conversion, try to understand. While we are doing this DC to AC transformation, during this DC to AC transformation, it creates lots of harmonics. Right? When we are switching this converter at very high frequency, so what will happen? High frequency noise will appear in the voltage as well as in the current. So shape of the voltage and current, that will not be sinusoidal. Or what we can do, if we have connected certainly some nonlinear load at the point of common coupling. I'll show you the next, coming block diagram or the circuit diagram for this system. So if I've connected some nonlinear load, why nonlinear load? Because nowadays the domestic loads, people are having huge energy efficient loads, right? The AC is coming with the inverter ACs. The other devices like lots of LED bulbs are there which are using this AC to DC and then DC-DC converters. Correct? So if I'm talking about these loads, they have been classified into two parts. Right? Let me tell you the loads, the nature of loads, so that you people get the idea why the nonlinear loads are considered over here. So if I'm talking about, there are two types of load, right? Two types of loads. One is voltage fed kind of load. Voltage fed loads. And another one is current fed load. So what are those current fed load? If I'm talking about the nonlinear loads. Nonlinear loads. So most of the majority of the loads you'll find out, even though you talk about the induction machine, right? Induction motor drive. So what is the circuit of induction motor drive? The front end converter is diode rectifier, right? And the front end converter is diode rectifier, which is supplied from the AC source, And the output side, we have capacitor filter. And then we are supplying to induction motor like IGBT, and then these inverters are supplying the power to the loads. So here you can find out the capacitor filter at the output of this diode. So this capacitor will make the voltage constant at this point, right? So if we have diode rectifier followed by capacitor filter, and let's suppose this has been considered as a, it should be considered as a RL load, but let's suppose we have some active power requirement here. So R we have along with this L load. Correct. So if you have this kind of structure or this nature of load, this is coming under the category of voltage fed kind of load. And you know the operation of diode. When the diode will conduct, right? Diode will conduct whenever the input supply voltage is more than the output voltage. Suppose E0 voltage is there, right? So the moment when diode starts conducting, for that portion of conduction time, we are getting the current, right? We are getting the current. So what is the shape of this current? Can you tell me what is the shape of this current? This is the peaky in nature. Discontinuous current, peaky in nature. The shape may be changed depending on the value of capacitor. But you can find out for some period of time we have the current, however, for another time period or another time we don't have current here. So this is the discontinuous current, and you won't believe the TSD of this total harmonic distortion of this waveform is more than 70%, right? More than 70%. So you can think about if we have induction motor drive in a plant, and not only one induction motor drive which is utilized in a particular plant. There are lots of induction motor drives for pumping applications, for feeding the power or to drive some mechanical loads, lots of applications, fan loads, right? Exhaust fan applications. These drives are utilized. And the moment when you will put, you will pollute the power grid because total harmonic distortion. Again, they have provided some standard for power quality as well. What is the power quality standard? We have IEEE 519. Right? It says TSD must be less than 5%. And here you are polluting the grid and the TSD is more than 70%. More than 70%. You can think about the kind of pollution you are sending, or I mean, whenever you are drawing the power or you are supplying to the grid. Now, second type of load, that is, they have diode rectifier. And what they have done, along with R, they have connected, instead of connecting a capacitor, they have connected heavy choke coil here. Heavy inductive coil they have connected at the output of this diode rectifier. So if I have high choke coil here, what is the shape of current? If the shape of current with R load is this, then the moment when you put the heavy inductor, this current will become flat, right? And the positive half as well as the negative half. So what is the shape of current for single phase circuit, right? Obviously for single phase. For three phase, it will become quasi square because 6 diodes are there and they are conducting in a different fashion. So what is the TSD for this square wave? What is the shape which is allowed from this supply? We can draw sinusoidal, or we can supply sinusoidal current to the grid, or we can extract the sinusoidal current from the grid. We're not allowed to extract the current this type or this type of current. It is not allowed to take these shapes of the current from the grid. So TSD of this square wave is around 48%, right? And what is our target? We have to reduce this 48% to 5%. Now, if I'm talking about, suppose, if I have chosen this diode rectifier, still I have not chosen a control rectifier yet. Try to understand. If I'm having a controlled rectifier, your output voltage will also decrease. So it will draw some kind of reactive power. But here, even though you have chosen simple diode rectifier and you have voltage in this shape, right? And even though current is a square wave, but the zero crossing of both these waveforms are same. So if I have this shape, and if zero crossing and peak are matching with each other, so power factor will be unity, right? It must be unity. Now, what is the power factor if I'm drawing a square wave from the supply? Can you imagine? If peak and this zero crossing is matching, it must be unity, right? It must be unity. But here the power factor is deteriorated due to these kind of loads. Even though the voltage, current is perfectly in phase with the voltage, but as the shape changes, the power factor is also deteriorated. So power factor is not now the power factor definition, which we are saying like it is active power divided by apparent power. Here the power factor definition become PF, that is your distortion factor, and DPF. Fundamental power factor, I would say. So fundamental current after filtration, that is in phase with the voltage. But rest of the current, it is appearing as a high frequency current, I would say, because now the current is changed. If you talk about the total RMS current, it is now I1 plus IH. What is IH? Harmonic current. High frequency current. I1 is your fundamental current. But what about the IH? IH is the harmonic current. So if transformer, suppose a transformer, it is rated for 6 ampere and you are getting 0.5 ampere from this harmonic current, total current would be 6.5 ampere. It will increase the total RMS current through the transformer. And if total RMS current is increased, what about the heating losses or I square R losses? There is significant increase in the heating of the transformer as well as the losses in the transformer. So we need to address such kind of issue over here. So the power factor definition, it is changed to DF. So it is not only a fundamental power factor which we are getting for RL or simple R load. Now the power factor definition, it is distortion factor and DPF. So DPF, displacement power factor, that is almost unity, but your DF, it is the ratio of your fundamental current with the total RMS current. Right? So fundamental current, suppose it is 6 ampere and total current is 6.5, nearly the DF which we are getting, that is 0.9, 0.8, 0.7. So if you put this 0.9 multiply by 1, the total power factor, even though the zero crossing of these two waveforms are same, right? Current and voltage, your power factor is decreased to 0.9 due to the harmonics only. Right? This is the detailed discussion regarding this non-linear load. Why this non-linear load deteriorating the power factor? Even though till now I have not introduced any control converter here as a load. If you have control converter, then only, then there will be a reactive power requirement and your power factor may further decreased. And then this converter not only address the power quality, this power factor correction, this also has to, supply some kind of reactive power so that the voltage at the point of common coupling can also be boosted. Right? So this is the second challenge which we have faced and we have addressed in our systems using adaptive control, intelligent adaptive control to address this power quality issue. We have used some adaptive control instead of simple DQ control. But why? Because in DQ control, it is, it works well under steady state conditions. Right? Steady state conditions or for linear loads, it is working fine. The moment when we have this non-linearity in load or non-linear load, this D component, it starts having some kind of ripple. Right? And which is directly appearing to the reference current, which I'll show you. And this reference current, if it got polluted, what will happen? Sometimes inverter switching may be wrong, right? Inverter switching signals which we are generating, they will be polluted. And if the pollution is there toward that side, so lots of EMI and wrong switching may happen to this converter. Correct. So we have to address these challenges here, like seamless transitions, which we have discussed. And the second challenge, which is very crucial to address during grid connections and this. So this way, the two challenges, I mean, we are going to discuss. So what is the motivation and objective for this? Like recently, MNRE has taken several steps to abutment of this diesel, because if you talk about the city like Delhi, right, you can think about the pollution level over there. So you cannot use these diesel engines and I mean to avoid the outage of electricity. The PV with battery and grid synchronization, desynchronization could be the good solution for residential areas. You can have a battery backup along with this PV. So in night, you can store the energy to the batteries, and I mean, if grid is there, you can take the power. And this type of system also well suited for variable tariff, right? Whenever the grid supply or the cost of electricity from the grid, it is more than the I mean, the energy which we are taking from the battery or from the solar, we can switch these component to the battery, to the grid, depending on the what are the kind of tariff which we are getting from the different components. So another important aspect, due to protection regions, the solar inverter, it is mandatory to shut down automatically at the loss of utility grid. Right? However, this system, it is switched to the standalone mode, right? From the protection region, what will happen in the solar inverter? So the mandatory thing with the solar inverter, right? We have to have this grid, otherwise this inverter, if we talk about the grid tied solar inverter, what is the mandatory condition? Grid must be there. If you have disconnected the solar this grid, you will, I mean, you will not be able to supply any power to the load as well as to the grid. Obviously, grid is not there, so there is no meaning to supply power to the grid, but you will not able to feed the load as well. However, when the system solar inverter, this grid disappears, under that condition, the system can can be operated in standalone mode, and the power can be supplied to the consumer loads. Right? Then the PVBSS microgrid systems, extracted active power is shared between load and utility. Moreover, this microgrid can be operated under outage of PV source and utility, which in turn increase the utilization factor of this PV and decreases the payback period of power converter. Right? This I'll tell you how we can decrease the payback period. Right? So in simple solar inverter, if we have this solar inverter and it is connected with the grid, what is the payback period of this? I mean, what is the utilization factor of this inverter? It is utilized only daytime because the sunlight is available only in daytime. But what we have done, if sun energy is not available, at that moment, this inverter, it is acting as a power compensating device. Right? So during this daytime, it is acting as a power unit, supplied power to the grid. In night time, you have connected some load over here, which is supplied from the grid, non-linear load, I would say, inverter ACs or some other loads. And this power can be fed to the loads via this, this compensating device can be connected, which will take care of harmonics and the quality of power which we are supplying to this, which we are taking from the grid. So what are the other benefits from this system? Reduction in the distribution losses. we have distributed small systems. It is not a centralized kind of system which we have with the long distances like 10 kilometer, 20 kilometer or more than 100 kilometers like. A small system which is situated at the home itself, right? Load is very near to the inverter end. So there is a reduction in the transmission and distribution losses. Enhanced utilization of installed distribution equipment. Bidirectional power flow capabilities is there. Means whenever sun energy is more than the load demand, rest of the power can be fed to the grid. Whenever the sun energy or solar is down, at that moment we can take the power from the electricity grid. So the bidirectional power flow is possible. No need of bulky magnetic transformer. We have used the simple bidirectional converter at the battery side. So this high frequency transformer we have reduced. Solar PV can also be directly coupled to the battery as well as UPS. Now, another important aspect, we have used static switches and the reliability of the system is improved. So static switches, which I was talking about in this case. So in between these two units, between the inverter and the grid, we have connected some power electronics devices. Instead of having circuit breaker or some other devices, we have power electronics devices which can be, the response of these devices is very quick as compared to your circuit breaker and other relays. Right? So indirect cost reduction by reducing losses and minimizing tripping, using the PV feed forward loop in current control mode, which gives the novel power distribution concept, right? PV feed forward to improve the dynamic response. I mean, we have used this PV feed forward loop in adaptive control. And the classification of this solar PV based microgrid, like we can have the single phase systems, three phase systems, and further we can have single stage and two stage. So basically, single stage, we are talking about in terms of power stages. Right? So in case of single stage, we have removed the DC-DC converter. Because generally you might have seen in case of PV array, we have this DC-DC converter and then this DC bus and then DC to AC converter. What we have done, we have removed this DC converter in one of the configuration. So you can say, how do you do this MPPT? So transfer of this DC into AC, that is done by this DC to AC converter. At the same time, we have achieved the MPPT as well. Right? MPPT is also achieved using this DC to AC inverter. So instead of deriving this reference, or we can say deriving the duty cycle for this converter, we have derived the VDC reference from this PV array. So what we have done for this MPPT algorithm, we have sensed the VPV, IPV, right? And it is going to the MPPT, and the output of this MPPT is VDC reference. And this VDC reference is given to this inverter. The problem is solved. I mean, instead of having losses, extra thing in case of DC-DC stage, we have only DC2. Instead of two stages, we have only one stage over here. So what is the advantage? The losses in the DC-DC converter, the overall efficiency of the system is improved. But what would be the challenge if you have single stage system? Anyone who can tell me the challenge in case of single stage system where this solar PV is directly connected with this solar PV array is directly connected through this converter and feeding the power to the grid. What would be the challenge? What would be the challenge in this case? So the blocking voltage, if you are a power electronics, I mean, you studied the basic power electronics, will be knowing the blocking voltage of this switch is decided based on the input supply, right? VDC. How much VDC we require? We require 700 volt VDC. According to this, we have to choose this switch. Here, this DC-DC converter, try to understand this DC-DC converter, it is used for the MPPT purpose, right? Because I mean, only one degree of freedom, whether it can do the MPPT or it can boost the voltage from, I mean, from the lower value to the higher value, right? Suppose boost converter we have used. Here, the purpose of putting DC-DC converter, we are not regulating the duty cycle or this D of this DC-DC converter more than 2. The duty cycle, it is always less than 2, because if you are boosting the voltage more than 20%, there is significant losses. There are significant losses in the DC-DC converter. So you are fixing the duty cycle. We are putting sufficient number of number of modules in series so that the duty cycle must be 0.2. It should not be more than 0.2. Because series, putting the module in series, that will decide the voltage. Right? So suppose one panel, suppose it is having a voltage of 32.9 or 32 volt. I have put 10 panels in series. So what would be the voltage? 329. Right? So accordingly, I'll put panel to get the desired voltage here. So near about 700 we have to get here. So what we will do, instead of putting 10 panel, we will put 22, 23 number of series panel here, the series modules here, and we'll get around 700 volt. So 700 volt VOC, try to understand. Once this moves to VMPP, right, this voltage will drop because you can see the MPP curve. Here we are operating at VOC, but as soon as it is tracking the MPPT and it is reached here, we are reaching to VMPP. So VOC is always greater than the VMPP. So this voltage, suppose the fill factor of this PV array is around 0.8, 0.9, like that, 0.95, whatever the fill factor, it will depend on the different manufacturer, right? So VMPP that we have here, so let's suppose it is reduced to 650 volt. So 650 volt, and what is the DC bus which we have here? That is 700 volt. So we have to boost this 650 to 700 volt within this 0.2 duty ratio. Now, what is the case in case, in single phase or single stage system? So in case of single stage system, the required DC bus voltage, right? Here we can maintain 700 volt by having a lesser voltage as we have fixed the duty cycle 0.2. So lower voltage can be boosted to 700 volt. Like I told you, 650 volt can be boosted to 700 volt. Now, can we have 650 volt here? If I have 650 volt here, what will happen? I'll not get 415 volt at the converter output. And if I'm not getting the converter output 415 volt, my per unit voltage, it is beyond 0.88. If it is within 0.88 to 1.1 per unit, then it will be successfully synchronized with the grid. But if it is not within the limit, it suppose further reduce beyond this limit like 350 or 300 volt, my converter output will not be synchronized with the grid. This is the main disadvantage in case of single stage system. So what would be the solution? We cannot keep same number of panels or same number of modules for single stage and two-stage system. So the disadvantage of single-stage system, we have to put higher number of series modules or parallel module, series modules, yes. Because parallel will give you the current value, right? Higher series modules in case of single stage system. So if I have, suppose, instead of fixing 700 volt, I'll fix 750 volt VOC, so that the 750 further it can be reduced to 700 volt, right? Like 50 volt drop was there reaching from VOC to VMPP. So 50 volts, so successfully I'll get the 700 volt here and I'll be able to generate the converter output voltage 450. So extra 2 to 3 panels I have to put in case of single stage system. That is the basic requirement. Right? So people are using this kind of concept in different way. What they are doing, they are saying this one as a central inverter. They are having different controller for different panel. They are optimizing the power of each panel and then they are feeding to them. They have a central controller, MPPT controller. They are optimizing whole the plant and then they are feeding this power to this central converter and to the grid, so on. So this is the way to have these two systems which they are feeding the power in a different domains. Like so if you ask, you told me two types of topology like single stage and two stage, but which one people should prefer? I have gone through various literatures and you won't believe, I mean, if they have quoted this two stage, they told like two stage system is very good. If they have quoted the single stage system, they are saying efficiency of the system is very good. And as the boost converter is reduced, so this system is, I mean, efficiency of the system is significantly improved. But what is the behind the scene? In case of single stage, we have to, initial investment is very high. You can see the number of panels which we require, that is there. So in case of now, as a conclusion, if you ask me, sir, according to you, which system we should prefer? So I will say it is a trade-off between these 2 points, these two systems. If you are able to invest little more money, I will suggest go for a single stage system because during longer period, it is very good. Reliability of the system is good as compared to the first system because here DC-DC converter, again, it has some component diode, some boost, and boost converter, 3 basic component are there: switch, diode, and inductor. However, here we get rid of this boost converter. So if we get rid of this boost converter, certainly the reliability of the system will be improved. Right? For longer period, I mean, if it lasts longer for 25 years and you are able to reduce some percentage of losses, then the overall generation will be very good. Right? So this is the trade-off between these two systems. And one of the major disadvantage, if you are choosing 750 volt DC bus here and the blocking voltage of these switches, which I didn't tell you, that will be decided based on the 750 volt. However, the switch rating which we have taken in case of DC, in case of two stage for DC to AC converter, that will be decided based on the 700 volt. So as soon as the blocking voltage is increasing, the cost of the switch is also increasing. Right? So as soon as you have larger device or the blocking voltage is more, the cost of the device will be more. So you have to invest. So there are two factors. You have to invest extra money on the number of panels. You have to invest extra money on the device rating. the selection of devices become important in case of single stage system. Further, people have different categorization like battery based, battery with biaxial converter, or directly it can be integrated with some kind of manual monitoring or some sensor they put, like if SOC is beyond certain limit, the battery will be cut off like that. So let's go to the first conventional two-stage single-phase topology. So what is there? We have PV array and these three components. So as I told you, it has only 1 degree of freedom, whether it can either it can boost the voltage or it can do the MPPT. So basically, the purpose is to use for MPPT purpose. I mean, to do the MPPT. Now, after this, it is converted in this DC into AC through simple inverter, PV inverter. Now, what is the utilization factor of this inverter? This can be utilized only in daytime. There is no scope to supply any power to the nighttime. So the utilization rate is only 6 to 8 hours. Because in nighttime, we don't have the supply out of 24 hours. Out of 24 hours, we are able to utilize only 6 to 8 hours because see, we should get the sufficient voltage here so that this inverter can generate sufficient voltage at the output of this unit. Otherwise, your grid will not be synchronized. So under low generation condition, when the generation is very low in the morning time, right? Sometimes inverter may not be switch on. It will be, tripping continuously. It will be tripped. So no, at low power generation, this inverter is not going to trip. And this has been realized, in real time conditions, right? So morning, if you are going to switch on, so you will not get enough DC bus here. Inverter will not be switched on if enough DC bus is not there because it is not able to convert this DC bus into the sufficient AC bus, which is getting the reference from the grid itself, right? So this inverter is controlled in current control mode. So the utilization factor is only 6 to 8 hours. How we can improve this inverter, right? So 2/3 of the day it is unutilized. What we can do? So what we have done, we have connected one load which has to be compensated here. And after this compensation, we have not invested anything in the hardware, only sensor, some load feed forward sensors we have put in the control, right? So load current, extra load current sensor we have put here. And this load current sensor, through load current, we are providing the reference to this inverter. So during night time, during daytime, it is feeding the power to the grid. So this unit is acting as a DC to AC. However, in night time, it is acting as a compensating device. Compensating device. Compensating device means because here you have connected a load which has to be compensated. So what we can do, load can be compensated from this supply. Non-linear loads we have connected so that the power factor, reactive power demand can be fulfilled from this inverter. So you can see we are not taking only one function here, which which we have seen in this particular figure. What we are doing, 6 to 8 hours, it is utilized as a solar inverter. After 6 to 8 hours, like if we are able to utilize like 8 hours as a solar inverter, rest of the time, right? 16 hours, we are utilizing this converter as a compensating device, right? We are utilizing as a DSTAT-COM, distribution. It is the distribution static compensator. It is taking care of power quality. It is taking care of harmonics, which is generated by the nonlinear. Now the question is, what is the demerit of this system? How we can improve the further utilization factor of this voltage source converter? Any idea? How we can improve the utilization factor? So these two topology which we have identified, these conventional topology, many researchers have given these two topology. Then we come to our research, right? So what we have observed, this system is not well suited for rural areas where there is continuously fluctuation is there. So if this inverter grid is cut off, right? Grid is disconnected from this voltage source converter, we will not get, or this converter utilization factor for that particular point, we are not able to switch on this converter. Utilization factor will be poor in that case. So what we have done, instead of controlling this converter only grid connection, grid mode, we have controlled this current converter in current control as well as in voltage control mode. During standalone, in current control mode, the voltage and frequency are well established because grid is there, right? However, when we are talking about the voltage control or standalone, we have to maintain, by generating some reference in the control, we have to maintain the frequency and magnitude at the point of common coupling so that the load gets the sinusoidal and constant supply. So what we have done, we have get this type of circuit, right? So we have used the single stage here, no boost converter, PV is connected here, and then we have voltage source converter, and then we have used some adaptive control here, right? Least mean square based family of this normalized least mean square based control we have used for current control, intelligent control, which we have talked about. And the switching between the voltage control and current control. So this is acting as a current control. However, this is acting as a voltage control. And this topology is given in this particular paper, like I told, transaction on test application. So this current control and voltage control, we are switching depending on the availability of the grid. Suppose grid is there, so we have to switch this converter in current control mode. And this type of operation is autonomous. It is not like that we are talking about the manually we are switching from current to voltage and voltage to control mode. It is autonomous system. It is switching from current to voltage depending on the grid condition. And similarly, on the other hand, I have also told you about this static transfer switches. So these static transfer switches also getting signal from the synchronization control, which I told you, like the limit of voltage, frequency, and theta. Right? So depending on the limits, if the converter output voltage, frequency, theta will match with the utility grid parameters, then this will be switched in grid connection mode. If these two limits are not matching, then the system will switch it to the voltage control. Now, what is the demerit of this system? Again, see, we have to go step by step, right? Research is all about how you are formulating your problem in a statement, right? Your problem statement, how you are formulating it. First, you have to find out the research gap in the existing systems, and then you can go for the systems which are, which can address a certain problems in the existing systems, right? So if you talk about this system, if grid and PV both are not available, suppose grid is not available, solar is not available, and grid is also not available, this emergency load cannot be supplied. This system will be shut down in that condition. So what we have done, we have connected a backup to these systems. So when PV and grid both are not there, these dynamic conditions we have tested in hardware as well. So if this grid utility grid, PV array, both are not there. In that case, battery will be discharged through this mode. This converter will act as a DC to AC again, right? And I mean, this battery, obviously, depending on the SOC level, this battery will be discharged. And what is the battery capacity? I mean, the discharge rate as well as the time, like backup hours, that will be decided based on the SOC level as well as the capacity of the battery. And here the converter is there, so it will supply according whatever the load you have switch on. According to that, it will supply power to the right. So this way we have these various design like boost inductor design and various this DC link voltage. How do we select this DC link voltage for single phase systems? If the grid voltage is 220 volt or 230 volt. So 400 volt voltage we have selected and discharging element of this battery. And this is the overall control of voltage source converter. We have voltage source converter. So this is the current control, right? Current control in grid connected mode. And this is the voltage control. As I told you, we have to regulate the voltage. So we have sense the load voltage and it is compared with the reference one. We must know how much reference we need to maintain the constant voltage at the point of common. And static transfer switches or solid state switches that will tell you whether I have to move to the current control mode, grid tied mode, or I have to operate in islanded mode or standalone mode. So according to this, the switching signals are decided, right, for this inverter, for this voltage source. Right, so let me complete quickly so that I can show you one simulation model for related to this. This is the simple mathematical equations which has been used to model this intelligent control. And then we have cascaded PI based battery control, like VDC can be regulated here. And then we have different battery current, like battery reference current, which is compared with the actual battery current. So what we are doing, we are sensing the DC bus voltage and battery current. We are not sensing the battery voltage. And cascaded PI is used. So outer voltage or PI controller is used to regulate the DC bus voltage. However, the inner PI control, it is utilized for IB, battery current regulations. And then we have generated this S1, S2 for bidirectional converter. And this is the mode shifting or static transfer switching, like voltage, frequency, and theta. If they are matching, then it is switched to the grid connected mode. Otherwise, it will operate in islanded mode. And this is the flow chart for energy management based microgrid, like monitoring of grid parameters, grid interactive mode, then if STS are activated, then shift to the islanded mode. And depending on the different SOC and other parameters, we have to feed the power to the utility grid as well as to the battery. So these are the few simulation results which I'm having here. You can see in the first figure is represented for outage of utility grid, right? So you can see till 0.4 second, the utility grid is there, grid current is there, grid voltage is there, both are out of phase. What does it mean? The power is fed to the grid. So the power which is available from the PV array, it is supplied to the load, and you can see load current is maintained constant. Load is not disturbed during outage and during connection of utility grid, right? So load current is getting continuous power, which is the main motive of this developing this kind of system. So voltage is also, become zero here. However, in next figure, you can see suddenly there is activation or there is appearance of the utility grid. So both the voltages are well synchronized, load voltage and grid voltage. Grid current appears, and again we are starts feeding the power to the grid. These are the harmonic spectrum which I was talking about. The total arm distortion is like 4.16, which is following the IEEE 519 standard. However, the load current TSD you can find out around 31.63%. And these are the response under steady state and outage conditions. And we have developed this experimental prototype using some auxiliary component like voltage source converter, PV array, and then other parameter. And here you can find out we are operating this at MPPT, right? And then certainly the certain these synchronization, certain appearance of the utility grid and outage of utility grid that we have derived in the experiment as well, right? The voltage and current are synchronized. So these are the few results. Here in hardware also you can find out the TSD which we are getting, that is 5%. And the voltage and current both are out of phase here, which means this negative sign shows like power is fed to the grid here. And then other control performance of this intelligent control like intermediate signals. So within a cycle, the signals are settled for this control under dynamic conditions. And these are the scenario under outage of both the sources, like grid outage is there. So PV source outage is there like here. And if both the sources are outage, you can see the battery discharge rate is increased because now battery is feeding power to the load, right? So VSC current is also increased because power is coming from the battery. However, PV current is 0 here. You can see the PV is at 0. So PV current is 0. However, battery is discharged to feed the load here. So same configuration we can do in 3-phase that we have seen in case of single phase. Same configuration we can realize in the 3-phase. So I'm showing this 3-phase configuration in MATLAB. Let me quickly share the screen and tell you how do we develop this MATLAB model here, and then we can have the question and answer, a session for this particular topic. So I hope my screen is visible for this MATLAB simulation, right? So you can see we have 3-phase grid. If I'm going from left to right, let me take and carefully see my cursor, right? So 3-phase grid, we are starting. So this is the MATLAB window, command window, where we are doing the different MATLAB. We are bringing different MATLAB blocks from the library. So we have 3-phase grid and certainly 3-phase impedance we have connected here. And then we have PES switches, power electronic switches, which I was talking about, right? So we have chosen these switches here. And then at the point of common coupling, we have chosen this as a non-linear load. So diode rectifier, which I told you, followed by RL. Here we have chosen this constant current type of load. I told you 2 types of load. One is constant current type of load. Another one is constant voltage type of load. So we have chosen constant current type of load, heavy inductor coil. You can see the value of inductor is 200 milliamp. So heavy choke coil is connected at the converter. Here we have VI measurement and then interfacing inductor. A 3-phase inverter is chosen here. And at the DC bus, we have connected this PVR, right? So again, you can see it is a single stage system. We have not added any kind of boost converter here. So as I told you, we are driving the reference here, right? So this is your MPPT block. We have taken VPV, IPV, and this is going to this MATLAB function. And the output of this MATLAB function, you can see here, that is VDC reference. Where it is going? It is going to the inverter control or in the bidirectional converter, right? So we have this inverter control, and this inverter control, we have taken this VDC here. So VDC reference, in case of single stage, it is not decided based on the grid voltage. It is derived from the PV array. Try to understand, right? So PV array decides this VDC reference in this case if you have single stage system here. So single stage system we can have here, and solar PV array we designed here in I mean, so modeling we have done for this PV array. We have the I naught current, IPV current, different. I mean, nowadays people are getting this directly. We can go to the MATLAB library. You just search solar PV array, you will get it. But here we have done the modeling, right? Different. We have model. How do we get the 32 like 400 watt or 500 watt panel here? That has been models. And by defining the number of series in parallel, we got the array. So there are three ways. Like initially we have cell is converted into module, then module is converted into array. By connecting these number of series and parallel module, that structures in a what we can say array. Right? So this way we have connected the overall system. Now let's go to the control one. So you have the control, two types of control, which I have told you. We have grid connected control and islanded control. So this is the grid connected control where we have sensed the load current. You can see load current is sensed, and this load current, it is passed through some advanced control. Right, some kind of filtering unit, filter or advanced adaptive control we have taken here. And this advanced control, it is giving the load component. And I told you during my talk, we are getting the PV feed forward term to get the good dynamic response. So here we have this PV power, and it is divided with the voltage, 2 PV by 3 VT. So we are getting this way PV feed forward term to improve the dynamic response. And then other side we have PI controller to maintain the DC bus voltage. Right? Simple PI controller we have used here. And again, we have decided like -20. And I mean, it will depend on how you are choosing these gains. So the net output is your active component, and this active component of the active component of this output, it is multiplied with the unit templates. And these unit templates are derived with the help of grid voltages, because you have to synchronize your converter with the grid. So instead of PLL, you can use the unit template. I mean, there are a number of control for synchronizing your converter with the utility grid. Whether you can go with the PLL, some advanced PLLs are also there, enhanced phase lock loop are also there, unit templates based control is also there. Right? So this way we can have this multiplication of unit template, then we can define the reference current. This reference current is matched with the actual current. Right? This reference current we have generated IAR, IABR, ICR. These three reference current are compared with the sensed grid current. So ISA, ISB, ISC, that are the sensed current and given to the hysteresis controller here. So this is the upper part, it is coming from the current control. Now you have the STS. So STS, it is defined based on these terms: voltage, magnitude, frequency, and these are the phase angles. Difference of phase angle we have taken sign so that the error between these two can be reduced. And they have been added in the AND gate and STS given to signal to the STS, right? So STS got the signal from here. And depending on the situation of STS, these two control will be activated. On the other hand, we have standalone control. So as I told you, we have taken this standalone control from the right. We have defined the voltage magnitude because we have to maintain the constant voltage at the point of common coupling. So the constant voltage we have taken, and this constant voltage is multiplied. So generally we have to make Vm sin omega t. We have to generate Vm sin omega t. So it is a three-phase system. We have generated for phase a Vm sin omega t. Second will be Vm sin omega t minus 120. Third will be sin omega t plus 120. So this way, three reference voltages has been generated. Once you have generated these three reference voltages, actual voltage will follow these three reference voltages. So let me show you the measurement block and let me run this system whether we are getting the appropriate results or not. So here to see this or to monitor the parameters, we have scope. In a scope, we can see this voltage, different grid voltage, load voltages, and then we have grid currents, and then we have load current, VSC currents, right? Output of this VSC current, then we have VDC. Like that. We have monitored different parameters. So if I open this scope, so what is the first one? First one is the grid voltage. So grid is recovered at 0.4. You can see grid is recovered at 0.4. Right? First one is grid voltage. What is second one? Anyone who can tell me what is the signal at second one? That is load voltage. Right? You can see the magnitude of these two voltages are same. But the difference is till the time even grid voltage does not appear, your load voltage is maintained constant. Right? There is no fluctuation which is observed in the grid voltage. What was that was our basic requirement or basic idea. In a standalone, we must maintain the load voltage constant. We are not allowed to provide any fluctuation in the load voltage. So load voltage sustained constant with the actual magnitude throughout the process. Whether your grid is appearing or grid is not there, even though at 0.8, you can realize the grid disappears. There is no change in the grid voltage. Load voltage. Load voltage is maintained as it is. Right? Now, the third signal is your grid current. Right? So grid current appears after a few cycles, once both the theta are synchronized, like theta, grid theta and load voltage angle, grid voltage angle and load voltage angle, both are perfectly synchronized, then grid current appeared. Right? And once the grid voltage is not there or grid disappears, your grid current also disappears. So during this, we program this particular simulation in such a way so that grid must appears between 0.4 to 0.8. Right? Only this period of time to test this particular system. Now the third one that is showing what is the third signal? Load current. It is in quasi-square shape because this is three-phase diode rectifier which we have chosen here. And we have also did the load dynamics. Load dynamics means in a standalone, suppose one of the phase is removed. So that has to be compensated. And here the inverter is supplying the fourth signal is the IVSC current. So you can see till the time we have standalone, only standalone power or the load power required by the load that has been supplied by this inverter. However, the moment when grid appears, your VSC current is increased because now it is operating in MPP mode. I told you the concept of off MPP mode and on MPP mode. So the VSC current is increased because now it is carrying the compensating power as well as the active power. So that active power will be fed to the load as well as to the grid. And we have the DC link voltage, which is regulating at the actual value, like we have chosen around 400 volt if I'm not wrong. And it is regulating with the different, it is almost constant, we can say. Right, so this way we have realized this simulation model, and same has been validated in the experimental as well. I mean, in the hardware as well. Correct. So this is all about from my side, right? So we discussed about different, concept related to topology and different concept related to this, systems. A detailed investigation, has been done related to grid interactive systems. Intelligent control has been proposed for the seamless transition under grid recovery and grid outage conditions. We have also addressed the power quality challenges, the total harm distortion, which we have limited, that is 5% under highly nonlinear conditions. So these are the few references which has been used for this work. Thank you very much. And if you have any question, you may ask. Because still the 20-minute time is left, so we can have some question and answer here. Yeah, that's all from my side. Yeah.
Sir, I have one question. Am I audible, sir?
Hello. Yeah. Mukul.
Yes, sir. Sir, I was trying
Yes.
the same thing in hardware. I was facing difficulty in setting the bandwidth in this hysteresis current controller.
Bandwidth. This will operate in variable frequency, right?
Yes, sir.
This relay or whatever you are saying, hysteresis controller, it works in variable switching frequency. So I don't know. I have chosen this bandwidth of this, like you are talking about the upper limit and lower limit, right?
Yes, sir. Yes, sir.
So upper limit and lower limit, you can choose any number which will be lesser than 1, like 0.001. That would be the upper limit, and lower limit that you can set 0.00 minus 0.001.
Okay.
I have run this system with different value of these upper limits and lower limit.
Okay,
right? So because it is a variable switching frequency, if you have constant switching frequency, you need not to set this band, right? Because you can simply have a duty cycle that can be compared with the triangular wave.
So one
But
issue
here,
yeah.
Yes.
Please,
Yeah.
sir, you continue, sir.
Yeah, so that way you can set the bandwidth there like 0.00. You should not leave this as a EPS. You should epsilon or some infinite bandwidth is there, but you have to set some bandwidth like 0.001 for a positive one, and the lower value you can set minus 0.001. I think it will work.
Correct, sir. Sir, I have one more question in continuation. My
Sure.
system with 80 volt of AC supply can provide me okay harmonics in the source current as a D-stat form. But whenever I go above my 80 volt of AC supply, currently I'm only using inverter. I haven't applied any PV or other things. My
Okay.
source current waveform starts deteriorating. They become worse.
Okay. So 80 volt, and what is the load which you have applied?
Non-linear, sir.
What is
After
no,
rectifier
current.
RL.
Yes. So what is the magnitude of load current?
The load current is around 6 ampere.
6 ampere, right?
Yes, sir.
During when you are drawing the power from the grid.
Yes, sir.
And when you are transferring the power, what is the magnitude of this grid current when you are
Currently,
transferring the power from the PV?
currently, sir, it's only inverter only. I haven't connected till now any PV or battery till now. Only this SATCOM.
Okay, so can you repeat the question? At 80 volt, you are
Of
getting
AC
the
supply, at 80 volt of
okay.
AC supply, my grid current harmonics are somewhat in range. Matlab they are little below the 5% or little above the 5%.
Percent.
But when I
Okay.
increase my source voltage up to 120 volt, my source current harmonics, they deteriorate with the same current, with the same controller, which I use, adaptive control.
So have you changed the DC bus voltage?
DC bus voltage.
Or
Yes,
DC
sir.
bus voltage was same? DC bus voltage was same for 80 volt as well as for 120 volt?
No, sir. For
What was the
DC bus
what was
voltage,
the what was the reference for 120 volt?
sir, DC bus voltage we have kept around 200 volts
For 120 volt.
for 120.
And for and for one this 80 volt,
Sir, around 150 around.
150, right?
Yes, sir.
So I mean, see, it should work. If it is working for 80 volt, it should work for 120 volt as well.
Yes,
Because
sir.
the moment when you increase the voltage, what will happen? Your current will also increase, right? The distortion may increase in one case when the magnitude of fundamental current is lesser than the, or it is very less, right? Let's talk about, we have 2 ampere of current, right? 2 to 3 ampere of current. And out of this 2 to 3 ampere, we have, because fundamental is fixed, right? And if I'm decreasing the total magnitude of current, my harmonics fundamental is varying, but the harmonics which I'm getting, that is fixed, right? So if I'll not increase the fundamental, if I'll not increase the fundamental value, my harmonic current will be dominating,
Okay,
right?
sir.
So what I have to do, I have to provide enough current, or I have to increase the load so that it should draw higher amount of fundamental current, so that the difference between harmonics and fundamental become larger. Otherwise, if harmonic current are dominating, suppose I'm talking about the load which we have 3 to 4 ampere, and you are measuring the harmonic current, obviously the harmonics will be dominating. So and that condition, you may not able to get the 5% or 6% THD. So my suggestion would be increase little bit load current. If you have that kind of facility, increase, go to 7 to 8 ampere like that, so that you will get the enough fundamental current, and the grid current TSB, obviously it will be improved.
Okay, sir. Correct, sir.
Yeah.
Thank you. Thank you very much, sir.
Yeah.
Thank you so much, sir. Hello. Sir,
Thank
I'm
you,
audible,
sir.
sir.
Thank you so much for the
Sir,
opportunity.
thank you so much, sir, for
Thank you.
taking time out for his busy schedule, sir, to lead today's session. Sir, your session was not only informative but also deeply enriching. I would like to thank you all participants for your active involvement, sir. So the next section will be conducted tomorrow, same slot at 5 p.m. onwards. Sir. Okay. So, thank you, sir. Thank you
Thank
so
you
much,
so
sir.
much. Thank you. Yeah, thank you
Sir,
for providing me this opportunity.
sorry
Yeah.
for interrupting. I am Harshavardhan, sir, from Triple department.
Yeah.
Sir,
Yeah.
actually, with the system you are having, how can we address the problem in grid resilience? Actually, can this be applicable to virtual power plants? If I take a small microgrids like that, this system.
So this is the microgrid only. If you can see, it can also support the grid in some extent, right? It is a great forming type of system because your load is getting power from the even when we have disconnected from the grid,
Yes, yes.
right?
Okay,
So this
okay.
is improving the reliability of the supply, even though when the grid is not there. So that
Yeah,
kind of
okay.
system we have developed to improve the grid resiliency.
Okay. So actually, when talked about resiliency, it is a sudden drop or it is like a interrupt only. Because resilience, we will address like with climatic changes. So solar is taken like that, sir. Here, can I take solar?
Uh, as a no, solar is renewable, right? Right.
Yeah, yeah.
Solar,
Solar
how
is
you can, right? You can feed the power to the grid using this solar. You can feed the power to the load.
under interrupted when it is power is interrupted.
Yes. So suppose I'm talking about the grid resiliency under these conditions, like there is sudden demand of active power from this grid. So
Yes.
at that duration, my renewable source can support the peak demand.
Okay. Okay. Okay.
Right, so it can withstand and quickly recover the conditions, because if you have certain suppose certain requirement from the power grid, what will happen, the extra burden will be put, so extra current will be drawn from the grid, voltage may collapse at that particular point. So you
Okay.
may have renewables or the battery bank which can support the power grid during peak hours, so that you can maintain the voltage stability and other factors during that.
Okay.
So
Okay.
this way we can address the grid resiliency. I mean, I'm
Okay.
I'm the power electronics guy, so I mean through this integration I can answer, but in the power system aspect, sorry about it. I mean, I cannot address
No,
this
no, sir.
question. Like,
It's okay, sir. Actually,
yeah, that's
my thought is like I want to develop a digital twin model, and I want
okay.
to go for a virtual reality. I want to use VR so that
Mhm.
the restoration can be done immediately. So
Yes, yes.
can I take this system? This is a microgrid system? So can I go for a replica of this system using digital twin?
Yes, yes.
Yeah.
Yes, similar system can be utilized, because here what we have observed, there is unexpected outage,
Yes.
and unexpected outage that can be addressed in case of grid resiliency.
Yes,
Sudden,
yes, yes. Yeah.
my grid system or grid must be withstand with these conditions. So if we have grid in combination with the renewables, that can
Okay.
withstand with the that can address the huge demand of active power, that can I mean provide, if you have these static converters, that can also stable the voltage, because reactive power demand can be fulfilled, frequency can be regulated, that can be
Okay.
addressed using these systems.
Right, sir. Thank you, sir. Thank you very much, sir.
Yeah. Yes, thank you for asking these questions.
Thank you so much, sir.
Thank you. So I would like to thank, MNIT for giving me this opportunity to interact with the participants, as well as I would like to thank all the participants who have essentially listened me for last almost 2 hours. Thank you, all of you. Thank you. Thank you so much.
Thank you so much, sir.